Okay, so I want to go through the worksheet on hypothesis testing. The very first question is, we want to convince the accreditation agency that our students are meeting the requirements. Some of the students are required to be proficient in a foreign language and second language, so we'll select 25 seniors at random and pay them to take a test for an hour on a Saturday, and we're required to have more than 80% of the students be proficient. Okay, so we need to write down a hypothesis to test, and then we're going to test it. So for the hypotheses, we need an H naught and an HA. And again, these are assertions, that's why those are colons. We're arguing about what percentage of the students are proficient. So it seems to me that we're arguing about P. This doesn't say P hat because we're not arguing about the sample numbers. We're arguing about if we didn't take a sample but instead did a census of every student, what would we get? Well, we're not going to take a census of every student. So instead, we're going to, we're going to take a sample, but we're then trying to use the sample to get information about the population. That's why these are population numbers. The argument is about the population. Whoops, I wrote an equals there. This is P equals 0.80, and this is also about 0.80. Got to be the same number in both cases. It's not really an argument if you're not talking about the same number. And the null hypothesis, the accreditation agency people are saying, I'm not sure you met the requirement. And what we're saying is, yes, indeed, we did meet the requirement. P is greater than 0.80. Okay. And we're reporting, it seems to me, when I go back and look at what we report, what are we reporting? Oh, we're going to report that we have a 21 out of 25 proficient. So we're going to report here P hat equals 21 out of 25, which is 0.84. Let me bring that up. 0.84. 0.84 is bigger than 0.80. Is it big enough that a person is convinced this is not just a sampling thing? Is there enough of a difference between 84 and 80 that we say to ourselves, okay, I guess that must be that I was wrong. The H0 people say it must be that I was wrong. Or is 84 close enough to 80 that it could be a sampling thing? So we got to test that. Got to test it. Okay, so you always test things the same way. You assume that H0 is right, because if you say to somebody, let's assume you're wrong, you're not going to persuade them. So you assume that H0 is right, and then you want to say to yourself, if I took many, many samples, the chance of my sample would be very, very small. So we got to get the distribution of samples. The distribution of samples looks like this, and I'm not a very good drawer. In a minute, I'll ask StatKey to draw it for me so StatKey can do a much better job. This is the distribution of P hats. So if we had lots and lots of people take a piece of paper out of a bag and we were able to see what would all the P hats look like, would ours be a way out sample or would ours be perfectly typical? So what's this centered at? Well, of course, we started off assuming that H0 is true. So we're saying to the people in the seats, you think that P is 0.8. And yeah, that's what we think. Well, in that context, if we take samples, then we expect that some people will get samples a little less than 0.8. Some people will get samples a little more than 0.8. In other words, this should be centered around 0.8. Okay. And then we want to find out where is our sample. So that is to say, we're going to find the p-value. So we want to figure out where is 0.84. What's the chance of something like a 0.84? So of course, I can't guess it. I have to ask StatKey. So here we go. So let's see, StatKey. It seems to be testing for a single proportion because we're arguing about whether P is 0.8 or not. So that's testing for a single proportion. Okay, fair enough. And the single proportion that we're arguing about is 0.8. So 0.80, 0.80. Okay. And at this point, I have to enter some data so the StatKey can do something with it. And I think that the data is 21 out of 25. Okay. Okay, now StatKey is going to find for us the distribution of samples by taking 1,000 samples. So I take 1,000 samples and I get 1,000 dots. Each of these dots, each of these dots, each of these dots. Every one of those is a sample. Okay, so we're asking ourselves now, is a point, in this context, is 0.84 a truly extraordinary sample, the kind of thing you only see one time out of 1,000, or is 0.84 a perfectly everyday sample? So we ask ourselves, let's find 0.84 in this graph and see what samples like that, where samples like that sit. Are they rare or are they common? So I clicked on right tail because it says greater than. It says p greater than 0.80, and I'm clicking on what's down here to make it to be a 0.84. 0.84. And what we see is that 0.84 is a perfectly everyday choice. 0.84 and samples like that and samples more extreme are perfectly common. In fact, it says 0.409. The chance, the p-value, the chance of getting a 0.84 type of sample is very, very high. It's like 41% chance. So what we're finding is that there's something like a 41% chance of such a sample. Well, that's not extraordinary at all. So when I go back to the piece of paper, what I'm finding is that this is 0.409. That's a perfectly everyday chance. These people say, okay, so you got a sample that had a perfectly everyday chance of happening. I think my contention that it's just a sampling thing is still very much alive. So we failed to reject. H naught. H naught says, well, you're just going to have to come up with better information than that. Your evidence is not strong enough to convince me. Okay. Okay, so that was the first example in on the worksheet. Let's try the second one. Okay, now we want to know if the math skills of the incoming SMC male students is less than the math skills of the incoming SMC female students. So we're going to give them a test, and we're going to test samples of each to check the proficiency percentages. So I'm looking at the percentage of men, percentage of proficient men against the percentage of proficient women. Okay? So I'm looking at the percentage of proficient men against the percentage of proficient women. So the null hypothesis and the alternative hypothesis. The null hypothesis is that the percentage of proficient men and the percentage of proficient women, that there's no difference. The null hypothesis always is that there's no essential difference here. So P1 minus P2 is 0. The alternative hypothesis is, though, we're wondering if the percentage of proficient men isn't less than the percentage of proficient women. So we think that might be less than 0. I think that because the question asked me to think that. Now, if you're more comfortable here writing P1 equals P2, and P1 is less than P2, that's perfectly fine. I got no problem with that. I like this way. There's two ways to do it. I like this way because then when I go to draw the sampling distribution, then the zeros are right there. So that's why I like it. But this is perfectly fair. That's absolutely fine. Okay, so of course, I got to report a number and test that data. So it says the men proved to be 7 out of 15 proficient, and the women proved to be 13 out of 15 proficient. Okay, so the men are 7 out of 15 proficient, the women are 13 out of 15 proficient. Now certainly 13 out of 15 is a higher percentage than 7 out of 15. Is it enough higher that you say to yourself, it's hard to believe it's just a sampling thing, or is it just perfectly possibly a sampling thing? Okay, so we got to do the test. The test always goes the same way. You assume H naught. And then you got to ask yourself, is the sample that I got so far out there that it's hard to believe H naught could be right? Or is the sample that I got perfectly every day? So I need to know what the samples look like. So then the sampling distribution is this. They always look the same way. Sampling distributions are always narrower than the underlying distribution, so I draw it as an exaggeratedly tall and skinny bump. And let's see, so what is it again? It's the distribution of P1 hat minus P2 hats. So if we had 1,000 people, each of them sample by putting papers in a paper bag and pulling out and saying, well, my sample is, and my sample is, and for my sample, I got this difference between men and women. For my sample, I got this difference. Then that's what we're looking at here. Zaki, of course, is going to do it. I'm not going to actually do it. Where should it be centered? Why, we assumed H naught is right. So we expect that some of the people pulling papers out of the paper bag will say, well, my sample is a little less than 0. And other people will say, my sample is a little bigger than 0. That is to say, we expect it to be centered around 0. Okay, let's ask stat key, what does it look like? Okay, so I got to back up. Too many buttons. I got to back up. It seems to me that of the hypothesis test that I have a percentage of men and a percentage of women. So I think I'm looking for the difference in two percentages. Indeed, the null hypothesis is P1 equals P2. That's what we want. So we're in the right place. And then I go to enter the data. And I've forgotten the data already. It's 7 out of 15 and 13 out of 15. So I lost Stacky. There it is. 7 out of 15, 7 out of 15, and 13 out of 15. 13 out of 15. Okay? So 7 out of 15, 13 out of 15. Looks like I hit the right buttons. And I get a P1 hat minus P2 hat of negative 0.40. Okay, so here we go. I'm going to generate 1,000 samples and see what the sampling distribution looks like. And it looks a lot like I sketched on the piece of paper. It's kind of a bell curve centered at 0. So going back to the piece of paper, I'm looking now to find what is the, look, I got this, and I'm looking to find what is the p-value. So on that, it's supposed to be the same graph as best I could draw it. I'm asking, this says less than, so I'm asking to look at an area like this, negative 0.40, and I'm asking myself, what's that area? So of course, I'm going to ask stat key what it is. Bring stat key up, and I've got to go to a left tail, and negative, oh, it came up with negative 0.400, and it says up there 0.025. So back to the piece of paper, back to the piece of paper. The p-value is 0.025. Now 0.025 is pretty low, 2.5%, pretty low. So the null hypothesis people are saying that P1 minus P2 is 0, and we say, well, we took a sample, and in the context of what you're saying, the sample had a very small chance of happening, only 2.5% chance of happening. And in particular, because that's less than the traditional 5%, I'm going to say that your contention is starting to be hard to believe. 2.5%, that's a pretty rare sample. So in that context, your contention is starting to be hard to believe. You're saying something which would mean that my sample was rare. So I'm finding it easier to believe that this is true than that this is true. So we reject H naught. In particular, we reject H naught because the p-value is less than the traditional alpha equals 0.05. Okay, very good. Okay, one more then. Drug delivery. So we want to make sure we're dosing, that dosing our drug nasally gives the same performance as dosing the drug in a pill form. So we select 12 people who take the drug, and to half we administer it nasally while the other half get it orally, and we see how the averages compare for the particular thing that this drug is supposed to do. Okay. So I need to go to the piece of paper, and I need to write down the null hypothesis and the alternative hypothesis. So it seems to me that the argument is about the average between orally and nasally. Which one came first? So I guess nasally comes first. So we're saying that the the average nasally minus the average orally, and again, these are population averages because I don't care about the sample. I want to know what would happen if we gave this drug to sort of everybody in the world who takes the drug. The null hypothesis people say there isn't any difference. The alternative hypothesis people say, you know, I think there is a difference. I don't know whether it has a larger effect or a smaller effect. I'm not sure, but I think there is a difference. Okay, so we've stated the concern. These folks are concerned, these folks maintain that there's no difference. These folks are concerned that there might be a difference. And then to run the test, of course, we always want to do the same thing. We always want to uh, uh, we always want to find out what's the chance of a sample that is of the kind that we got, and we're always going to ask stack key. So what happens is we report that for the nasally administered, we get these numbers. That's a typo. That's not supposed to be there. For the nasally administered, we get these numbers, and for the orally administered, we get these numbers. I got to enter those in stack key and see what stack key says. But I'm looking at a difference between two samples, and I'm looking at a difference between averages, not percentages. So I find myself on stack key looking for the difference between two averages, whereas before I was looking at the difference between two percentages. Okay, the null hypothesis looks right. It's average 1 equals average 2. And now I've got to enter the data. And it comes out in awful small letters, but let's see if I can enter the data correctly. This is the hard part. Come on. Come on, there. No. Cut. Okay. Okay, now I got to enter the data. So I'm entering this data for nasally administered. So I'll copy it from the slide and see if I can manipulate it right. So n comma, n comma, oh darn it, it's 64. N comma, n comma, n comma, and n comma. Get rid of the period at the end of the sentence. Okay, now I'm going to enter the oral, so 56. Okay, see how I do here. Okay, so this is oral, comma, oral, comma, oral, comma, oral, comma, oral, comma, and darn it. Okay, I think I did that right. Oh, okay, I think I did that right. So, so now, I mean, I'm just gonna ask stack key to generate 1,000 samples and see what the sampling distribution looks like, and it looks like a bell curve. So back I go to the I'm going to test by assuming H0 is true. Okay. Then I get a distribution of samples. And they always look the same. It's centered around 0. And it is the distribution of x1 bar minus x2 bars. And I want to know how far off is my particular answer. So I don't remember what my particular answer is. When I go back to stack key, my particular answer seems to be 11.33. So I want to know how far off is 11.33. Is it a quite rare one? Is it a perfectly everyday one? Okay, so back to the piece of paper. So we ask, what is the p-value? And this is the only tricky part. Okay. I did get 11.33. So I am asking about that region. But I asked up here for unequal. So I'm just as concerned about being down 11.33 as I am about being up 11.33. So I'm also going to write negative 11.33 and find that region. I want to know, the calculation here is to find the minimum of those two sizes and double it. So you find the minimum area and double it. Find the minimum area and double it, and that'll be the p-value. So let's ask StatKey, what is the minimum area, and double it. So for the right tail, I want 11.33. 11.33. Okay, and it comes out to 0.002. Pretty small. For the left tail, I want negative 11.33. Negative 11.33. I want to find the area, and it comes out to 003. Again, pretty small, a little bigger, but still pretty small, 003. I take the minimum of those two, that's the 002. Take the minimum of those two, so that's 0.002, and double it to get 2 times 0.002, which is obviously 0.004, and that's the p-value. Because the p-value is very small, I'm going to reject H0. It's, of the two choices, it's hard to believe this because the sample is so rare that it's easier to believe this is true than it is to believe this is true. Okay, so we reject H0. So the only thing that's different is that in the unequal case, you have to consider the left tail and the right tail. You take the minimum of the two and you double it, but so you end up with still a pretty small p-value. Okay, very good.